Okay, so we're looking at statics with rigid bodies. So that's things like ladders and planks and so on. So rather than just particles. So in this case, we've got a uniform rod AB of mass 40 kilograms and length 10 meters. Rests with the end A on rough horizontal ground. The rod rests against a smooth peg C where AC equals 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. And then we're going to find the magnitude of reaction at C and the coefficient of friction between the rod and the ground. So first thing we want to do is get a nice diagram, and then we can sort of see what's going on a little bit. So we've got the rod AB, which is going to be something like this. A's on the ground, so B must be up here, and we're told that is 10 meters long. So let's make a note of that. I'll draw the ground in as well. We've got an angle of 15 degrees here, and there's a peg here, which is C. And then we've got to label all the forces that we've got going on here. So there's going to be a reaction force at C. So I'm going to label that N for the normal reaction force. There's going to be reaction force at A. And I'm going to label this one R. So the ground's rough, so there'll be friction. So if you imagine this rod resting on the ground like this, if it was going to move, it would be sort of slide down there. So the friction wants to oppose that. So the friction must be pointing this way. Then we've also got the weight of the rod as well, which will be in the centre of the rod because it's uniform. So the weight of the rod will be 40 G. Because that's in the middle, that's going to be 5 meters from A. We were also told that C was 8 meters from A, so let's just label these things on. Okay, so what we want to do is then resolve some of these forces. So the first thing we need to do is work out the magnitude of reaction force at C, and we can do that by taking moments about A. Because if we take moments about A, then these two forces, R and F, they won't have any impact on it because they're going through A, so therefore they have no turning effect. So take moments about A. So we've got the 40 G force, well, producing some kind of moment on A, and then the reaction force at C will also have a turning effect, so producing a moment. So we want to get the 40 G force split into components. We want the component that's perpendicular to the rod to work out the turning effect. So that angle there is 15 degrees. So this component here will be 40 G cos 15. Okay, so when we take moments about A, 40 G cos 15 will give us a positive moment, but we're going to assume clockwise is positive. We could do it the other way around, it doesn't actually matter. This one's going to give us a negative moment. So we're going to have 40 G cos 15 times by the distance from A, which is 5. Then the normal reaction force is going to be a negative, and its distance from A is 8. And that needs to then equal 0 because it's in limiting equilibrium, so it's not actually rotating. So we've got an equation that we can then solve to find what n is, because 40 G cos 15 times 5 is just a number, and we'll just need to divide that by 8 to find what n is. Okay, so that comes out as being n is equal to 236.6518274. I'm making a note of the whole thing because we might need that number later, or roughly 237 newtons. Okay, so the next thing is to find the coefficient of friction between the rod and the ground. So the whole point about that is that what we want to do is find R and F, because once we know what R and F are, we'll be able to get the coefficient of friction because we're in limiting equilibrium, so F equals mu R. So to do that, we want to resolve forces somehow. So we can either go horizontally, vertically, you can go parallel and perpendicular to the slope. In this case, I'm going to go horizontally and vertically because actually we've got two vertical forces. We've got one horizontal one. It's only this one which is at a funny angle. So that n, I can split it into components. So this vertical component, well, this angle's 15 for a start. So that vertical one is going to be n cos 15. The horizontal one, which is going to go that way, is n sine 15. This diagram's getting a little bit cluttered, but hopefully you can see that. Okay, so if we resolve vertically, we've got r going upwards, we've got n cos 15 also going upwards. And then we've got 40g acting downwards. And because it's an equilibrium, that must equal 0. So r will be equal to 40g subtract n cos 15. And we can use our value from earlier to then calculate what that actually is. Okay, so I get 163.41188 newtons for r, or about 163 newtons. And then I can work out what F is in a similar way, this time by resolving horizontally. So resolve horizontally, F's going to the right, I'll take that as a positive direction. The only other horizontal force is n sine 15, and that's going the opposite way, so I want to subtract that one, and that's equal to 0. So F's just equal to n sine 15. I can use the value for n that we calculated earlier. Okay, so that comes to 61.2499999, or about 61.2 newtons. Then, I'll turn over now, because we've got limiting equilibrium, we actually know that F equals mu r, so limiting equilibrium so F equals mu r, and so I can just substitute the values for F and F and R into here, and then that's an equation for mu. Okay, like so. So all I need to do is then divide the 61.2 etc. by 163 etc. and then that will be the answer. And that gives me a coefficient of friction for mu as being 0.374819715. I'm actually rounding that to 3 significant figures to get 0.375. And that's it.